in from the rocks of Antarctica with the marine productivity, you get ages that are contaminated to be very old ages. Okay? So if we look at these, we can boil this down to two fundamental questions. How can we improve the understanding of core chronology? Because if we want to start to look at all of these data, all these paleo ice streams, and get a regional context of the stepping back of these glaciers, rather than just a few points here and there, we need to be able to depend on sediment cores that don't contain any foraminifer, because it happens a lot. Okay? And then the other interesting question is, what chronology can we pull from even below the grounding line? If we can really get rid of this old contamination, can we get some more information? And what we've just built here, and we actually have it running as of this week, is what we call the dirt burner. This is the Rent Pyrolysis C14 system. And to make this brief, we stick our sediment into a helium flow in a furnace that's variable. We step that up at 5 degrees per minute. And as we do that, the most reactive stuff starts to break down first, and it gets sucked down in the helium stream into the second furnace, which we just keep at 800 with oxidizing agents. And we oxidize everything to CO2. And we then collect the CO2 over different temperature intervals and date that as our radiocarbon date. So we're turning one bulk date where you're dating all the garbage that washes into the sediment all together with what you want to date, and we're trying to separate it based on the diagenetic stability. And the theory here is that what comes out of the water column is going to be less stable than what has been sitting on Antarctica for millions of years and has been washed down through sedimentary cycles and diagenetically altered. That's going to come off at the higher temperatures. And our first application of this method, we took sediment from right above the grounding line and we split it into 9 different temperature intervals. So this is temperature on the x-axis. This black curve is our CO2 evolution over the different temperatures. And then with each different interval, I have a different width of a bar here that corresponds to this right-hand side axis in radiocarbon years. And you can see that we take one layer of sediment, which in your geology textbook has one age, and we show that it actually has 9 different ages that vary 10,000 years between the highest and the lowest. And what's more important is that the ages keep getting older and older as we get into higher temperatures. So that's sort of a proof of concept that we have this diagenetic stability is related to thermochemical stability. At this point, the take-home message is that if you want to trust one radiocarbon date, this is your uncertainty, right? 10,000 years. The analytical uncertainty on this type of date can be as low as 15 years, but it means nothing. The geologic uncertainty is shown by the variability in these ages on this axis, and that's an important take-home message. But there's even more that can be taken from this method. One thing is that generally what we do, if we start looking at ages down a core, if these are bulk acid-insoluble organic matter ages, this is a 4M age, they're generally, the 4M ages, if they're available, are generally lower or younger than the bulk organic material ages. What's even more interesting is that the surface of the sediment that's collecting today, if you grab that and date it, it's usually going to be very old. It's not going to give you a 0 age. And it's going to be older than the reservoir age of the water. And this is because you have the combined effects of reservoir age, bioturbation, and old carbon contribution. And that old carbon contribution is what's eroded off of the continents. The common remedy is to just take that offset at the surface, assume that to be 0, and then take the same amount of age from all of your samples in depth. And in this case, this works. It seems to work, and it may be for the wrong reasons, which I'll show you in a second. I'm going to step back to our original paper, and what we did here was we took a few other cores besides that proof of concept one where we did 9 different ages. And here you can see our red is our data, the CO2 data through time. This is a sediment core. We have one at the top of the sort of subice shelf and one at the bottom of the subice shelf. And you can see that the shapes are different. And we modeled these in terms of a very simplistic model of Gaussian curves contributing to those bumps that you see. And we didn't constrain the Gaussians in terms of the centers, the widths, or the heights. That was left completely unconstrained. And what you see is that the Gaussians end up matching, the best fit Gaussians end up matching in terms of their centers, but they change in terms of their width and their heights. If these can be interpreted as different constituents of the organic material, like for instance, one of those might be the old stuff coming off of the continent, and one of those might be the primary productivity, and then we is that earthquake? We can assume that this means that down core, there is a different contribution of the different constituents. which, what I just told you, the assumption of constant down core old carbon is probably a bad one then. And what you can see here, the same data that I just showed you before, if you apply the ramp pyrolysis, which is now shown in triangles, you can see that at the top of the core, the age spectra are fairly narrow, but as we get down into the bottom of the core, and this is all through the same lithology, we get very high, relatively high age spectra here. And we can still use this technique to match fairly well with the 4M dates. But it shows that the proportion of pre-aged carbon is changing down core. And we can model this with sort of two end members, and the end result is that down core there's 3 to 4 times as much old carbon being incorporated into this core and contributing to that old age offset. And so it's sort of a warning to collaborators in the field that keep doing that. Here's another example of where we go through different facies all the way into that subglacial. There's an age offset here of about 14,000 years, and that's basically because you get into this low carbon environment where most of the carbon is coming off of the continent. If we apply ramp pyrolysis here, and we only did about 3 per, this was in the nascent stages of our work, we decreased that by about 30%, that hiatus. And if we had done 9 or 5 or instead of just 3, we probably would have brought these right into line with each other, which you would expect. And that leads to some interesting work that my student Christina Supt is doing now with, in collaboration with Korean colleagues from their icebreaker. This is submarine sediment on top of sub-ice shelf, and then we go back to submarine sediment. So this is a strange place for us to be in. And Michel Guittard with Amelia has some of the same facies from the other side of the Antarctic continent. The question is, are these a different marine isotope stage? Are they radiocarbon dead or what? The bulk age is about 31,000 years, which is nearly radiocarbon dead, but if we apply the ramp pyrolysis to it, we get an age of about 24,000 years, which is a lot smaller than these ages. And these have very high error bars because we're near the end of the radiocarbon timescale. So this was not drawn by my 3-year-old. This was drawn by me. I have a little work to do on it, but this was something that Dave Hollander wanted me to do. He wanted me to make a sort of tree of work that we've done from our original proof of concept paper here using the ramp pyrolysis. I've only talked about one branch here, the sediment chronology branch. We've applied it to the oil spill, sort of an environmental chemistry branch. We have 2 publications out there. We have just pyrolysis and method development, of course, in the middle. We have carbon cycle on these branches, which soil carbon and river transport of carbon, which are very important. We have a few publications that are out and a few that are in the pipeline here. So it's an exciting time to be working on this this method. So where are we then? Clumped isotopes, I'd say we're a little bit more advanced down that roller coaster. We're heading down towards the pessimism phase, but it's still an exciting proxy to say the least. Ramp pyrolysis, I think we're still in the optimism phase, but since we have so many branches we're working on right now, each of them has sort of a different position on here, which I can't really get into. One thing I would add to the students in the room is that if the thought of getting into a thesis where you're going down this slope into a pessimism phase is scary, it shouldn't be scary. This should really play to our innate skepticism as scientists in this room, that if you're not proving yourself wrong, then somebody else is going to, right? So we really have to expose our own warts and figure out how to best live with them. It's just great for developing that self-skepticism that all of us scientists need, right? So at that, I'll take any questions.
One.